With solar being such a key feature of Aptera's design, pretty much everyone wants to know how accurate is their claim of up to 40 miles per day. If you're an Aptera fan, you've likely used the savings calculator on the Aptera website. If you're like me, then the experience has probably left you wanting more details on how well Aptera's solar will perform throughout the year where you live. In this video, I'm going to show you how you can calculate a more accurate and detailed set of solar power numbers using a free add-on for Blender that I've developed. With this tool, you'll be able to precisely calculate the amount of solar power range for any location, date, time, and even vehicle orientation. You may be wondering, what is Blender? Well, Blender is a free open-source software tool for 3D modeling which is extremely powerful. It's the same tool that Aptera Motors has used to design pretty much their entire vehicle. All those pretty photo renders that you've seen of Delta were created using Blender. It's also the tool that I've used to design the 3D model of the Aptera for the Experience Aptera website, where you can view a full-size Aptera in augmented reality. If you haven't tried that out yet, check out the link in the video description below and give it a try. Blender also has a scripting engine that can be used to create custom functionality using a programming language called Python, which I've used to create a solar calculator for the Aptera. This calculator will allow us to visually characterize Aptera's solar power for a specific latitude and longitude, on a specific day, at a specific time of day, or over a complete day. With this power number, we can then use Aptera's estimated efficiency of 10 miles per kilowatt hour to determine how many miles you can drive on free solar energy per day for any day of the year. With a little bit of spreadsheet analysis, we can also determine an estimated annual range while taking into account cloud cover for your location. Now, before we get into the actual tool, let's talk for a minute about solar efficiency in general. This will help us understand how the Blender add-on works. If you have, or are planning rooftop solar for your house, you've probably run across various online calculators for predicting what the solar output would be for your particular installation. Like this one from the U.S. Department of Energy called PV Watts Calculator. These calculators take into account variables like your geographic location, system losses with the hardware, the compass direction your panels face, and the pitch angle of your roof. These last two determine what's called the incident angle of the sun in relation to the solar panel. This incident angle is hugely important in determining the efficiency of a solar panel. Let's take a quick look at a simulator that illustrates this clearly. Here there are several sliders. For this example, we're going to ignore the panel efficiency and atmospheric absorption controls, and set those to 100 and 0 accordingly. The sliders that control the angle of the solar panel and the angle of the sun are the ones we'll focus on. Together, these two determine the incident angle from which you can get a panel efficiency number in percent here at the bottom. You can see that to get the most electricity out of a solar panel, you want the sun hitting perpendicular to the face of the panel, or at a 0-degree angle of incidence. When this happens, the panel output is 100%. The greater the angle of incidence, then the lower the electrical output will be. Going all the way to a 90-degree angle is where the output reaches 0, since no sunlight is hitting the panel. If you were to plot the efficiency from this calculator from 0 degrees to 90 degrees, you end up with this curve here, where you can see that it ranges from 100% efficiency at 0 degrees to 0% efficiency at 90 degrees. While these calculators work great for rooftop solar, where they're designed for situations where you have 1 or 2, maybe even 3 different surfaces that contain solar panels, they can't accurately calculate the solar output for the Aptera, because on the Aptera, there are 193 individual solar cells that all face in different directions. Each one is going to have a unique incident angle to the sun, and therefore a different efficiency number that contributes to the total electrical output of the vehicle. We need a tool that can look at all of these same variables, but analyze each individual solar cell based on its incident angle. This is what my Blender add-on does, so let's take a look at it. This is Blender, and as you can see, there is a lot going on here. But fear not, even if you're not familiar with using Blender, there is really only one view that is used with the Aptera Solar Calculator add-on. There are 2 files needed to run this, the add-on installation file, and the blend file that contains the 3D model objects. At the end of this video, I'll show you how to get this set up, but for now let's jump right into it. When you start Blender, you're presented with a view containing some default objects, a cube, a camera, and a light. Go straight to the File menu and open the provided 3D model blend file called Aptera SolarCalc.blend. No need to save the default objects. This will load the Aptera into the viewport sitting on a ground plane. One of the first things you'll want to do is to change the viewport shading mode from the default solid mode to render mode, which is done by clicking the rightmost button in this set of 4 buttons in the upper right corner. This may take a few seconds to render the scene depending on the speed of your computer. In render mode, you'll see a more photorealistic view of the scene, with the Aptera sitting on a compass pointing east. By the way, the 3D model used here is the same model that is used in the Experience Aptera app, but somewhat simplified. For instance, it doesn't have any windshield or side glass for reasons I'll explain in a minute. The control window for the Aptera Solar Calculator add-on sits on the right side of the viewport, under the tab titled Aptera. It's likely that when you first load the blend file, that this control window will be hidden. To make the control window visible, press the N key on your keyboard to toggle the display of what is known as the N panel, that is this set of tabs on the right. Press N to display, press N again to hide. The controls for the Aptera Solar Calculator are added to the N panel when the add-on is installed. If you haven't installed the add-on, then the Aptera tab won't be there. Other important controls to learn are how to move around in the viewport. By pressing and holding the middle mouse button, you can rotate and change the viewing angle of the scene in 3D space. Holding down the Shift key along with the middle mouse button allows you to move the objects in the scene. Using the scroll wheel on your mouse will zoom the scene in and out. Knowing these navigation commands will come in handy when using the add-on to examine closer the position of the sun in the sky and shadows on the Aptera. On the very right side of the screen is an outline of all the objects used in the scene. You can see that aside from the Aptera itself, the ground, and the sun, each of the individual solar cells are its own object, all 193 of them. The position of the sun object is controlled by an add-on that comes shipped with Blender called Sun Position. This add-on positions the sun in the sky corresponding to the geographic location, date, and time that you enter. You can see that by changing the time of day, the sun moves across the horizon from east to west. You can also see that by changing the month of the year, the sun travels higher or lower on the horizon. Now let's go through the add-on controls. At the top is where you enter your geographic latitude and longitude. This is easily obtained from Google Maps. Let's enter the location of Aptera's headquarters in Carlsbad. If we search for Aptera Motors and right-mouse click on the drop pin, we'll find the latitude and longitude values. Now we'll just copy those into the add-on. Next is the date and time you want to analyze. Let's look at the longest day of the year where we'll generate the most amount of power, the summer solstice. So we'll enter 21 for the day, 6 for the month, and 2023 for the year. You also need to enter the UTC zone for the location, which in this case is -8. There is a button to check if this location falls under daylight savings time. The time value can be whatever you want, and we'll choose 1 p.m. Keep in mind the time is entered in 24-hour format, so we enter 13. The next section is where you select the vehicle direction. You can rotate the Aptera in either a clockwise or counterclockwise direction 22.5 degrees for each click of the button. Note that you can only rotate a full 180 degrees in each direction before it locks, and facing east is the default starting direction. The solar output section has a user-defined value for percent system losses. For this we're using a value of 6.81%, which is the value recommended by the PVWatts calculator for system losses after adjusting for those areas that don't necessarily apply to the Aptera. Although you can enter any value you think is appropriate here, or if we learn more detailed specifications from Aptera Motors, then this number can be updated. There is a button for including the dash solar in the calculation, which I'll come back to in a minute. There are 2 buttons for calculating projected solar power. The first one is Calculate Kilowatts, which determines the amount of power generated for a specific time of day. When clicked, the add-on will look at each individual solar cell and determine the angle between its normal, which is a vector perpendicular to its face, and the direction of the sun's rays. It will use this angle to determine the percent efficiency using the graph we looked at earlier. We know from the Maxion data sheet that the maximum output of each cell is 3.72 watts at standard test conditions, so the add-on will multiply this by the incident angle's percent efficiency along with the overall system losses to determine each cell's contribution to the total output. Here in this example, on this day at 1 p.m., with the Aptera facing east, all 193 solar cells will generate a combined 630 watts of solar power. I can quickly show you what the normals of the solar cells look like by temporarily making them visible. It's done by selecting all the solar cells, going into edit mode, and turning on normals. You can see how the angle for each of the 193 cells varies, with each one having a unique incidence angle and therefore a different percent efficiency. Let's turn that back off. The second button is Calculate Daily Kilowatt Hours and functions similarly in terms of its calculation, but assumes that the kilowatts generated will continue for 1 hour, which turns it into kilowatt hours, because 1 kilowatt of power over 1 hour is equal to 1 kilowatt hour. When clicked, it will automatically advance the time by 1 hour while cumulatively adding the kilowatt hour values together over the course of the day. Let's walk through an example. Start by setting the time for the first hour after the sunrise for that day, in this case 6 a.m. Then click the Calculate Daily Kilowatt Hours button continuously until the end of the daylight hours. Each time the button is pressed, the energy in kilowatt hours is calculated and added to the previous value. By ending at 9 p.m., which is the first hour after the sun is below the horizon, we balance out any power we miss by starting with the sun above the horizon. For this example, we calculate 5.778 kilowatt hours for the day, which then, using the projected 10 miles per kilowatt hour that Aptera is promoting, equals 57.8 miles of range for that day. There is a reset button at the very bottom to reset the energy value back to zero when starting this calculation for a new day. There is one more thing that needs to be accounted for, that is the solar cells on the dash. Because of the placement of these and angle of the surface that they sit on, there is a chance that they could be shaded by the roof of the Aptera. This is different than the other solar cells that sit on the exterior surface of the vehicle, which will naturally fall to zero efficiency once they reach a 90-degree angle to the sun. The solar dash may be less than 90 degrees to the sun, but shaded by the roof of the vehicle. You can see this in our example if we closely watch the sun's shadow starting at around 4 p.m. If we move the sun past this time, you can see how the shadow forms on the dash and obscuring the sun's rays from hitting the solar cells. This is why there is a control provided to include or exclude the dash solar in the calculation. Therefore, the proper way to calculate the daily kilowatt hours is to monitor the shadow and uncheck the box when appropriate. Let's redo our analysis for this day, but this time make it more accurate by excluding the dash solar when appropriate. We'll reset the kilowatt hour values, set the time for 6 a.m., and make sure the include dash solar is checked since the dash is unobstructed in the morning facing this direction. We'll click through until we get to 5 p.m. Then we'll uncheck the control to exclude the dash solar and continue clicking the button until the end of the day. This time we get 5.697 kilowatt hours, or 57.0 miles of range. This is slightly lower than the previous calculation by 0.8 miles, but likely a more accurate projection. The direction the Aptera is facing will determine exactly when this process of excluding the dash solar may need to be done. You just need to keep an eye on the shadows on the dash, which, by the way, is the reason why there is no windshield on this 3D model. Because of the way rendering is done in Blender in this mode, it was too difficult to see the shadow when the glass was in place. Now let's calculate the solar power that can be generated on an annual basis. For this, we'll need to build a quick spreadsheet where we can keep track of the numbers across a complete year. I've created a spreadsheet here with a simple table where we can get representative miles per day numbers for each month of the year and extrapolate that out for 365 days. I'm going to use the 21st day of each month and calculate the daily kilowatt hours for that day as an average for that month. One of the reasons for using the 21st day is because that coincides with the summer and winter solstice dates on June 21st and December 21st respectively. These are the longest and shortest days of the year. Let's start with January 21st, calculate the daily kilowatt hours, and add it to our spreadsheet. I'll speed this up while I run through each of the remaining months and fill out this table for the Carlsbad location. The cell at the bottom of the table calculates the average miles per day across the 12 months. The next cell below that calculates the miles per year by taking the average miles per day in the cell above and multiplying it by 365. As you can see for Carlsbad, this works out to be an average of over 41 miles per day and over 15,000 miles per year. But we're not done yet. So far what we've done is calculate the theoretical maximum solar power and range in miles assuming there are no clouds throughout the entire year. But unfortunately that's not the world we live in. Even here in sunny California, we get clouds and overcast skies on many days of the year. So we need a way to account for that percentage of time when the sun is obstructed. The way we can do this is with data that is available on the NSRDB, or National Solar Radiation Database website. This is a free site that allows you to get historical weather information for any location on Earth, which includes historical cloud cover data. Let's grab the latest year's data that is available for Southern California. Starting from the home page, we'll go to NSRDB Viewer and enter a location. We'll input Carlsbad, California. Then select Spectral On Demand for the data set. We'll select 2021 for the year, and 60 minutes for the interval, which is the only option. We'll also go with the default one-axis tracking. You then need to enter an email address and click the download button. After a few minutes you'll receive an email from NSRDB that says your download is ready, and a link to where you can download your file. The download file is in zip format, so you'll need to extract the CSV file and save it to a folder. Opening the CSV file, you'll see lots of data, but there are only 5 columns we're interested in. We also don't need the first 2 rows, so let's delete those. The columns we need are the year, month, and day columns in A, B, and C, the data labeled Clear Sky DNI in column H, and the DNI data in column M. DNI stands for direct normal irradiance, which is a standard measure of solar energy when the sun is perpendicular to the solar cell. The Clear Sky DNI is the total irradiance assuming no clouds in the sky, and the regular DNI is the actual irradiance measurement taking into account any cloud cover. We'll use these 2 numbers to calculate a percent loss for the historical cloud cover and apply it to our estimated solar generated power. Let's grab the data we need from the download file by copying the columns we need from this worksheet into a new worksheet. Once the data is copied, we can delete the first worksheet to save some file space. You'll notice that there are quite a few rows where the Clear Sky DNI is 0. These rows represent non-daylight hours, and we need to remove them. The easiest way to do this is to sort the data by the Clear Sky column, then highlight the top set of rows where the value is 0. And right-click to delete. Let's then resort the data back to the year, month, and day values to get it back to where we started. Next, we'll add a column that we'll call Cloud Multiplier, and in here we'll build a formula that calculates a percentage difference between the Clear Sky DNI and DNI. We actually want the inverse of this, so we'll subtract that percentage value from 1. Let's format this column to display percentages to make it more readable. To summarize with an example, let's say there was 10% cloud cover. We would then want a multiplier value of 0.9 that we can apply to our solar output power value. So you can see on days with no clouds, the Clear Sky DNI and DNI numbers are equal. The multiplier is 100%, or 1. On days that have clouds, the multiplier is less than 1. Now we'll determine the average across each month, so let's add a place to do that. I'll create placeholders for January through December off to the right. We'll create a formula to calculate the average for the month of January by looking at all the cloud multiplier values, where the month equals 1. We'll need to repeat that for the remainder of the year. I'll speed this up while I do that. You can see from the numbers how we are closer to 100% during the summertime, when there is less rain in Southern California, and a much lower number during the wintertime during the rainy season, which is what we would expect. Now let's copy this number set to our other worksheet table. Now it's simply a matter of multiplying these two together to get a forecasted annual amount of kilowatt hours and range. We end up with an adjusted daily average of 31.3 miles per day and an annual range of 11,441 miles. It's also interesting to see the highest monthly average is 41.3 miles per day during the summer, although that drops considerably by December at 13.7 miles per day. An important thing to keep in mind is that while we used historical data for cloud cover, we only used 1 year's worth of that data. To get a more accurate number, it would be good to look back over several years and get an average, so that may be something you want to try on your own. Now that we have a pretty accurate forecasted solar range number set, how does that compare to the Aptera calculator on their website? For a location like Southern California where you have a high average local solar exposure, their calculator says 28 average miles per day, while we calculated 31.3. Are there factors where we can improve our forecast? Yes. For instance, we aren't taking into account any shadows from trees or buildings. But overall, I believe we can be more optimistic in our expectations for solar range with the Aptera. Either way, this was a fun experiment and provides more confidence that Aptera can make solar mobility a reality. For an additional data point, I've done the same calculation for where I live in Northern California near Sacramento. Here are those results. Being farther north, I receive more sunlight during the summer but less during the winter. Another significant difference, though, is that we receive very little cloud cover during the summer months, with the cloud multiplier being in the 90s for 6 months out of the year. You can see that my solar range in Northern California would be less during the winter but more during the summer, for a higher yearly average of 33.3 miles per day and 12,169 miles per year. Another interesting thing you can do with this solar calculator is determine which is the most optimal direction to park an Aptera to maximize its solar charging capability. Should it be parked facing north, south, east, or west? I won't spoil the answer to that question. You'll have to calculate that on your own. But here's a clue: it varies for different months of the year. So how do you get a copy of this to use for yourself? I've provided a link in the video description below for instructions on how to download and install this Aptera Solar Calculator add-on for Blender. Clicking that link will take you to this page which outlines the steps needed to install the add-on. Try it out for your location, and let us know in the comments below what you came up with.